afternoon, everybody. Hope you're all healthy and safe at home. Let us continue with our chapter 4 on bounded linear operators. So in the previous lecture we had done the lemma 4.3.3, and now we'll be moving on to a proposition, the proposition 4.3.4. Let's see what it states. It states that the set of compact operators from x to y. So till now we were dealing with this compact operators, what is meant by compact operator, and when does an operator become compact, and so on. So here we are considering a space of a collection of compact operators, okay, and just like we had done in case of bounded linear functionals and so on. So here the set K of compact operators from x to y, it satisfies the following three conditions. The first one is it forms a linear subspace of L of x to y. It is a linear subspace of all bounded linear maps from x to y. That is compact set of compact bounded operators forms a subspace of bounded operators. The next one is if A element of K and B element of L of z to x, okay, and C is an element of L of y to z, then AB element of K of z to y and CA is an element of K of x to z. That is, if A is a compact operator and B is a bounded operator and C is a bounded operator, and correspondingly the mappings, that is A is from x to y, B is from z to x, and C is from y to z, then AB is also a compact operator and CA is also a compact operator. And the third one is K is a closed subspace of L of xy. The first property was that it is a linear subspace of L of xy. Then if we have a compact operator A, then for operators B and C, AB and CA also forms compact operators itself. Also, the third one is the set of compact operators, which is a subspace, is actually a closed subspace of L of xy. So let's see the proof of this proposition step by step. So the first one is we need to show that the set of compact operators forms a linear space, right? So K is a set of compact operators from x to y. Okay, we need to show that K is linear subspace of the set of bounded operators from x to y. So clearly K consists of operators or functions from x to y, and L also contains the subspace concept is clear. We just have to check the linearity, right? Clearly it is a subspace of L. We need to show that it is linear. Okay, so let us take two operators. Let A and B element of K. Then A is a mapping from x to y and B is also a mapping from x to y, and also A comma B are pre-compact or relatively compact. Okay, so these are the things that we have. Now with the help of this we are going to prove that it is linear. Now consider MA plus B. Okay, clearly it will be a map from x to y, there is no doubt in that. It will be a mapping from x to y, we need to show that it is compact, right? We need to show that it is compact. So let xn be any bounded sequence in X. Okay, then we need to show that it has a corresponding, you can find a Cauchy's subsequence. So let xn be any bounded sequence in X. Now m a plus b of xn can be written as m a of xn plus b of xn, right? Then what we have is, by definition of a and b, a of xn and b of xn, both of them has a Cauchy subsequence, right? Why? Because a and b are both pre-compact and xn is a sequence in X. So by definition of compactness or relatively compactness, we can say that if xn is any bounded sequence, then a of xn has a Cauchy's subsequence. So both a of xn and b of xn has Cauchy's subsequence. So let us see, let sequence yn and zn be the Cauchy's subsequence of a of xn and b of xn. Okay, if yn and zn are Cauchy's, then myn plus zn is also okay. That's the property of Cauchy's sequences. So this myn and zn will be a Cauchy's subsequence, and of which sequence will it be? It will be a Cauchy subsequence of xn, right? So m a plus b of xn also has a Cauchy's subsequence, and thus m a plus b is pre-compact. So we have chosen an arbitrary sequence and we have proved that correspondingly we can find a Cauchy's subsequence. That was the first part of the proof of the proposition. Now let us move on to the second part, that is a is an element of k of x to y, b is an element of L of z to x, and c is an element of L of y to z. Now we need to prove AB and CA are elements of K from corresponding. They are also compact. So let's see what will be the mapping AB. AB will be a mapping from Z to Y, and what will be CA? It will be a mapping from X to Z, right? X to Z. So clearly they are mapping from Z to Y and X to Z. We just need to show that they are pre-compact. Okay, so for that let us see the first one. Let us consider AB. Let Zn be a bounded sequence in Z. Okay, now B is bounded operator. So as Zn is a bounded sequence, B of Zn will be bounded. Okay, it will also be bounded. Zn is a bounded sequence and B is a bounded operator, so B of Zn will be bounded and it will be bounded in X. Okay, now so B of Zn is bounded, so what will be A of B of Zn? A is a mapping from X to Y, so B of Zn is bounded sequence in X and A is compact, so A of B of Zn will be having a convergent subsequence. Okay, thus AB is pre-compact. I hope the concept is clear. AB will become pre-compact. So how did this proof go? We need to show that AB is pre-compact. So for that we chose a bounded sequence in Zn, and as B is a mapping from Z to X and Zn is a bounded sequence in Z, so B is bounded, therefore B of Zn will also be bounded. And where will B of Zn lie? B of Zn will lie in X. Okay, so we have got a bounded sequence in X, which is B of Zn. Now A is a compact operator from X to Y and B of Zn is a bounded sequence in X, and since A is compact, this A of B of Zn will have a convergent subsequence, thus AB is pre-compact. In a similar way we can prove that CA is also pre-compact, so you guys can just write it down and check whether it is true or not. So now let's move on to the last portion of this proposition, that is we need to show that K is closed, right? K is a linear subspace. We need to show that this is closed, that is the space of all compact operators is closed. So for that, let us take a sequence An in K such that An converges to an operator. So An is a sequence in K means An, this sequence is collection of compact operators, right? And let us suppose that An converges to A. Now to show that K is closed, we need to show that A is compact. We need to show that A is compact. So once we show that A is compact, K will clearly be closed. Now to show A is compact, what we are going to show is, to show that A is compact, we shall show, we have done this before, we shall show that A d of x is pre-compact where d of x is the unit ball. Okay. Is the unit ball. So this is how we are going to proceed in our proof. Now one more thing that we have to keep in mind is that to show A is compact, we need to show A d of x is pre-compact, and by using the previous lemma to show that A d of x is pre-compact, to show A d of x is pre-compact, it is enough to show that what was the previous lemma that we had done? Enough to show that for every epsilon greater than 0 there exists an epsilon net in A d of x. This was the lemma that we did in the previous lecture. Okay, so let's see, we just have to prove this. Now as an is converging to A, we get for all epsilon greater than 0 there exists n belongs to capital N such that norm of an minus A is less than, say, epsilon by 2. Again, I am marking this as equation 1. Now sequence an was an element in K, so this implies an is pre-compact, right? So sorry, an is not pre-compact, an is a compact operator, and so an d of x, where d of x is a unit ball, will be pre-compact. Okay, so as an is an element of K, an will be compact, and so an d of x will be pre-compact. Okay, and again we'll use this previous lemma. So an d of x is pre-compact, so for every epsilon, this implies for every epsilon there exists an epsilon net in where an d of x. Okay, don't get confused with a of d of x. We have to prove this result is true for a d of x, but we know that this is true for an d of x. So let's see what happens. Now let set yl be an epsilon by 2 net of a and d of x. We have stated that a and d of x is pre-compact, so it has, for any epsilon it has an epsilon net. So I am choosing epsilon by 2 and I am letting yi to be the epsilon by 2 net of a and d of x. So this implies for some element yi dot in the set yi, we have norm of yi dot minus an of x will be less than equal to epsilon by 2. I am marking this as 2. Okay, so let me choose y an element of a d of x. Okay, so by definition of a, we can find an element in d of x. There exists an x element of d of x such that y is equal to a of x. Okay, that is y is the image of x, right? So this is by definition. So I'm just writing, instead of choosing y, I'm choosing an element y in a d of x, and I can write y as y is equal to a of x. Okay, so now let's see what happens to norm y minus yi dot. Okay, y is nothing but a of x minus yi dot, and now I'm going to add and subtract an of x. A of x minus an of x plus an of x minus yi dot. Okay, and by the property of norm, what do we get? That norm of y minus yi dot will be less than or equal to norm ax minus an of x plus norm an of x minus yi dot. Okay, now this is less than epsilon by 2. This is how we had chosen, because an converges to a, and we had chosen that this was our equation 1, and this is by equation 2. We get these both are equal to less than epsilon by 2, and so their sum is epsilon. Okay, so yi dot was an element of the epsilon by 2 net of an of d of x, and we have obtained that for any y element of A of D of x, norm of y minus yi dot is less than epsilon. So this implies this yi forms an epsilon net where in A of D of x. Okay, if we choose an epsilon by 2 net of A and of D of x, we can say that that forms an epsilon net in A of D of x. So this implies A of D of x is pre-compact by our previous lemma, and as A of D of x is pre-compact, we get A is compact. So we had chosen an arbitrary sequence an in K, and we have obtained, and if we assume that an converges to A, we have obtained that an converges to A and A is a compact operator. So that was our proposition. The set of compact operators is a linear subspace which is closed of L of xy, and A and B correspondingly, if A is a compact operator and B and C are bounded operators, then A, B and C are also compact operators. So that's it for today's session. Thank you, and stay safe.